Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you like my videos because they are interesting and important to your studies, also please don't forget to subscribe. So here is series of problems on cables. Level 26 on cables. The cable AB supports a uniformly distributed load of 180 newtons per meter. Determine the maximum force in the cable and the distance h. So here is the given figure. So since the slope at the endpoints A and B are given and the cable is treated as parabolic because the uniform load is distributed over the horizontal projection, then we can resolve the tension at B into two components, vertical and horizontal. The horizontal component is denoted by big H, and it is the tension at any point, horizontal tension at any point on the cable. So the maximum tension is expected at B because it is the highest point, and we solve that by force triangle and then by sine law as shown in the figure. So this is the tension at A, tension at B, then the equivalent load here is 180 times 20 and it acts at the centroid of this rectangular loading. So its distance from the right is 10 and from point A horizontally is also 10, half of 20 meters. So by force triangle we have 180 times 20, then this is tension A. So since it makes 20 degrees with horizontal, plus 90, so this is 110 degrees. Then this is tension at B, which is expected the maximum force, maximum tension in the cable. So again, this is 110. This angle that tension B makes with the vertical, with the horizontal 50, so with the vertical 40 degrees, 90 minus 50. And therefore this angle is 180 minus 110. 80 minus 110, 180 degrees minus 110, 70 degrees minus 40, 30 degrees. So this is 30 degrees. So by sine law, tension at B, which is maximum force in the cable as to sine 110, equals 180 times 20 as to sine 30 degrees. So the maximum force in the cable can now be computed. This will be 6766 newtons. Then for the distance h, we can find that by summing up taking moments about A. So vertical component of tension first, this will be sine 50 degrees times 20 moment arm. Then this is minus and this is minus. So minus the horizontal component of tension, 6766 cosine 50 times h. Then minus 180 times 20 times 10 moment arm equals 0. So the only unknown here is h. So looking for h. H is 15.24 meters. So that's it for this problem. Level 27 problem. A power tug is towing a barge with a cable which has a mass of 14 kg per meter of its length. It is observed that the tangent to the cable at point A is horizontal. So determine the tensions at A and B. So this problem, this cable is catenary because the given mass per meter is the weight of the cable, the uniform weight of the cable. And it is not mentioned it is projected upon the horizontal, although you can approximate it as parabolic cable because the sag to span ratio, the sag is 5 meters and the span is 65 times 2. Remember, this is the lowest point because the tangent is horizontal at A. But I'm not presenting it here. you may consider it as your exercise problem by treating this as parabolic cable. Anyway, the answer uh, will be close or expected to be close, but the accurate analysis is this is catenary cable. So since this is the lowest point, the origin is below point A, as shown. Then we will call this is always called C from the origin to the lowest point, and this is 5. So the tension at A is simply W times C. In general, tension is WY for WY, where W is the uniform weight of the cable and Y is the distance from the x-axis to the point. So Y is C cosine hyperbolic x over C. So Y is C at B, for example, is C plus 5, and x is 65 because this is the origin. So C plus 5 equals C cosine hyperbolic of 65 over C. So using the calculator, C is 423.33 meters. Therefore, the tension at A, which is the minimum tension denoted by big H, is W. W is 14 kilogram per meter times 9.81 to convert it to newtons. So T is WY. So H, or this tension at A, is W 14 times 9.81 times C, which is 423.33. So Y at point A, the lowest point, is just C. So tension A is H 58140 newtons, while at B the Y is C plus 5. So tension at B is equal to 14 times 9.81 times 423.33 plus 5. So tension at B is equal to 58830 newtons. So remember that the answers must be reported to 4 significant figures. So that's why the answer here is 58830 and not the displayed value in the calculator, to maintain the condition that I should report the answer to 4 significant figures. In fact, for some other authors, they just report the answers to 3 significant figures. Level 28. A uniform cable weighing 50 newtons per meter is suspended from points A and B. Before, the force in the cable at B is known to be 500 newtons. So calculate the force in the cable at A and the span L. So this problem is very much related to previous problem. So since the cable, the weight is 50 newtons per meter, so this is treated catenary. There's no condition that this loading is projected upon the horizontal, and though we do not know yet the span, so this is analyzed as catenary. Therefore, we superimpose the x and the y axis, which is below the lowest point, as shown. So knowing the force at B, the tension at B, so we have tension equals W 15 times Y, and Y at B is C plus 8. So from there we can solve for C. Then the tension at A is C plus 4, since C is already known from tension at B. Then we can compute the tension at A. Then apply Y equals C cosine hyperbolic of X over C to solve for XA, then also for XB. Then finally, we can solve for L, which is XA plus XB. So this is C plus 8, YB, and this is C plus 4, YA. So tension equals W times Y. Tension at B is W times YB. So 500 equals 15. So that's XA and that's XB. So 500 equals 15 times quantity C plus 8. So from here we can solve for C. C is 76 over 3 meters. Then tension at A can now be found. So the force in the cable at A, tension at A is equal to W15 times C plus 4, C plus 4. So tension at A is equal to 440 newtons. Having found the tension at A, then we use Y equals C cosine hyperbolic of X over C. So first, let's solve for XA. Y is YAC plus 4. 76 over 3 plus 4 equals 76 over 3 cosine hyperbolic of XA over 76 over 3. Solving for XA, so 76 over 3 plus 4 over 76 over 3, then inverse hyperbolic cosine of that ratio. Then the answer multiplied by 76 over 3, then that is X sub A. So X sub A is 14.055 meters. Then YB, which is C plus 8, 76 over 3 plus 8 equals 76 over 3 cosine hyperbolic of XB over 76 over 3. So quantity 76 over 3 over 8 divided by 76 over 3. The answer should be in the calculator inverse cosine of that answer, then times 76 over 3, that's X sub B. So X sub B is equal to 19.638 meters. So finally, we can compute L. L is 14.055 plus 19.638. So L equals 33.69 meters. Level 29. The light cable has zero slope at its lower point of attachment and supported the unit load which varies linearly with X from WO to W1 as shown. Derive the expression big H, which is the tension at the origin in the cable. So here is the given figure. It consists of loading which is projected upon the horizontal, but the loading is varying from WO to W1. So in this case, since this is the lowest point, the tension here is horizontal. This is the highest point, so the tension there is maximum. And we will denote the tension here as big H. Then I divide the loading into two triangles. So tension at A. Then I divide the loading into two triangles so that this is the area of the triangle, which is 1/2 of L times WO, and its distance from the right from A is 2/3 of L, as shown in the figure. Then for this triangular loading, the area is 1/2 L times W1, and its location from A is 1/3 of L, the location with centroid. So simply we derive H by summing up moments about A. So big H clockwise positive, big H times H equals 1/2 of WO L times 2/3 of L plus 1/2 of W1L times L over 3. Simplifying, big H times small h equals WO L square over 3 plus W1 L square over 6. Dividing everything by small h, so big H equals WO L square over 3h plus W1 L square over 6h. Then simplifying by factoring out L square over 3, L square over 3h. So L square over 3h, 6h rather, times 2WO plus W1. So that's the expression for H. Let's make it simple. So L square over 6h times 2WO plus W1. Although the original answer here is different in shape from the author's answer, but if you simplify the author's answer, it will lead to this simpler answer. This is from Miriam, the book by Miriam and Craig. Then that's it for this problem. Level 30. The cable of negligible mass is suspended from the two fixed points shown, and the tension at the lower support is sufficient to maintain zero slope of the cable at that point. So again, the tension at the lowest point is 0, so therefore we will denote that by big H. The cable supports a unit load W, which decreases from 100 newtons per meter at x equals 0 to 40 newtons per meter at x equals 30 meters. So with the decrease proportional to x square. So meaning this is parabolic. This curve is parabolic. And we call this spandrel of parabola, where the area is 1/3 of the dimensions, 30 by, of course, this is 60. 100 newtons per meter minus 40 is 60 newtons per meter. So it will be shown later. So the requirement is to determine the equation of the curve assumed by the cable. So for that curve, we first solve for the horizontal component of tension at this lowest point. So this is the imaginary extension, so that we treat this as the loading as rectangle, so that the location of the centroid is readily known. Then minus this spandrel, or if we treat downward loading positive, so this is upward. And the area of this is 1/3 of 30 times, as I said, 60. That's spandrel of parabola. So this is H, then we have tension at this point A. We'll call that point A. This is the lowest point. We may call that as point O. Then the equivalent loading for the rectangle, I treat this as whole rectangle. Area of rectangle is 100 newtons per meter, the uniform load times 30. And its location from A is, of course, half of 30, 15 meters as shown. Then this is upward because we treat this as whole rectangle. So therefore, it should be countered by this spandrel of parabola. The area is 1/3 of 30 times 60. 1/3 of 30 times 60, where 60 newtons per meter is this, 100 minus 40. And its location from centroids, remember, is x over 4, or 30 meters over 4, and that is 7.5, because that's second degree. First degree, if it is a triangle, then this is 30 over 3. For second degree, it is 30 over 4, that's why 7.5 meters. So summation moment about A equals 0, H times 10 plus 1/3 of 30 times 60 times 7.5, then equals or minus 100 times 30 times 15. So equals 0, so or equals 100 times 30 times 15. So we can now solve for H. H is 4050 newtons. Having found H, then we can now derive the equation of the cable by considering the loading up to distance x, as shown in this free body diagram here. So we cut, and this is x in general, and we will solve this W later by squared property of parabola. So that's 60 newtons per meter, 100 minus 40, so 40 plus 60 is also 100. Let's call that W. This is x, and we can derive W by squared property of parabola. So this is y shown. That's point P. The tension in general there is T, and this length is x, which is already shown here, and this distance is y, as shown in the figure. So we sum up moment about P. This is the horizontal, this is the value of H, and we have loading here, which is in general 100 Newton per meter times x for the rectangular loading, and it should be countered by this upward force of spandrel parabola 1/2 of x times W. By the way, that distance is x over 2 because this is a rectangular loading. The centroid is 1/2 of x, and for this spandrel, the value is 1/3 of xw, and this distance is x over 4, as shown in the figure. So summation moment about p equals 0, 4050 times y plus 1/3 of xw times x over 4, then equals 100 times x over 2. So simplifying, 4050y equals 50x squared minus 1 minus wx squared over 12. So to derive w, we apply squared property of parabola. W as to x squared equals 60 as to 30 squared. So w as to x squared equals 60 as to 30 squared. So w therefore is equal to x squared over 15. Substitute here. 4050y equals 50x squared minus x squared over 15 times x squared over 12. So finally, divide everything by 4050. So 4050 equals 50x squared minus x to the fourth over 180. So finally, divide everything by 4050. So the equation of the cable is x squared over 81 minus x to the fourth over 729,000. So the cable is a 4th degree curve.